Hey, I wanted to talk to you some more about MOSFET biasing. If you haven't watched the 6321 Homework 3 2015 video, you should, because this is based on that. I'm going to extend it. This was a cascode current mirror, low voltage current mirror design problem. All the V effectives were 0.25 volts. I wanted to make sure you understand about the PMOS biasing and several other things that we can talk about. So here we have a diode connected PMOS device, and it's got a constant current source, so its VGS is fixed. And we can see that if we come down from, let's change this to 5, the numbers will be a little easier, and run it. So we see that the voltage here, the V effective is 0.25, the threshold voltage was minus 0.5, the VGS then, all the terms are in the same direction, they're all negative, the magnitude is 0.75 volts, so 5 minus 0.75 gives us this voltage here. The voltage of the VGS of this, from here to here, magnitude is also 0.75, so this voltage is about 1.5 volts below the positive supply. This voltage at the source of M3 is the voltage at the gate plus the magnitude of the threshold, which comes down from here by 2 VGSs, comes back up by 1 VGS, so this voltage ends up being systematically matched to this, which is nice because now the 1 plus lambda VDS terms for M6 and M4 are matched. So if I can just kind of illustrate something here, if I grab all of this stuff right here, all of these voltages just move up and down with VDD. So if I increase VDD, for example, to 10 volts, then we expect all the voltages to go up together. And lo and behold, this one is higher, this one is higher, and this one is higher. Notice that this one comes up from the negative supply. So this voltage does not change as I raise VDD. But everything else stays pretty much the same. Another thing to look at is the effect of the bulk effect. I'm just going to edit this file. I'm going to delete a couple of wires. I'm going to add a couple of wires if I can remember how. Wire, wire, here to here. So I'm getting rid of the source to bulk ties and replacing them with the normal connection of the source, the bulk terminals all to VSS. If I run this again, notice that this was at 8.5 volts initially. If I run it again, it actually comes down some. So the moral of the story here is that all the terms in the threshold voltage increase with bulk effect. They're all in the same direction. They all add in the same sign. Now, a question we could ask is, what is the minimum value of this voltage that we could have? And that's determined by whether or not M3 is in the active region. It's got a 0.85 volts here, and it needs V effective of 0.25. 0.85 plus 0.25 would be 1.1. So we could drop this voltage so much that this could come all the way down to 1.1 volts. Now we can come down from that by 0.75, back up by 0.75, and back up by another 0.75. If you go through the arithmetic, I believe, let me just see if my memory is good, but you can do the problem as an exercise, and lo and behold, I can go all the way down to 1.85 volts here. That comes down to 1.1, down to just a very little bit here, and then back up to 1.1. So in principle, this should work, and just puts M3 at the edge of the triode region. And you could run this and make sure it works. Maybe we wouldn't want to go quite this close. Let's go back up and give ourselves some room here. Let's see, we originally had this at 3.5, so let's leave it there. All right, let's talk about the NMOS. Now, in the NMOS side, the VGS of M1 is the 0.6 threshold voltage plus 0.25 or 0.85. And we talked about this in the last thing, that the exact value doesn't work, but if we have feedback, that this thing will work. But let's look at the range of values of this VG2. We have this sort of in the middle to make sure there's room for M1. If we raise the value of VG2, let's raise it to say 1.5 volts, then when we run this, this voltage comes up, but it doesn't come up as much as we raised the VG2, and that's because of bulk effect. This thing goes higher, this thing comes up some, but that raises the threshold voltage of this, so it doesn't come up as much. And we remember that the gain of the source follower with an input to this gate and an output from this source is systematically less than 1 because of bulk effect. Now, with this at 0.85 and this is about 0.5 or something like that, we can raise this a little bit more, but if I raise it too far, 1.7 or something like that, I have a feeling that's going to be too far, then this voltage will come up, and now we have only 0.2 volts of VDS for M2. So that's too far. We've put this into the M2 in the triode region. On the other hand, we can't go too low, as I remember 1.2. Let's see if that isn't too low. If this is at 1.2, this thing comes down. Actually, this is just about right for the lowest we could make VG2 and still keep M1 in the active region. If we go any lower, then the VDS of M1 will be less than its V effective. Let's put this back at something reasonable. What do we have? 1.325. All right, so that's what's going on there. Now let me do a trick. I'm going to interpret this as the input side of an NMOS low voltage current mirror. So what I want to do is duplicate this side, move it over to here somewhere. I think this is about right. Then I'm going to grab a hold of this whole diode connected object, and now I can flip it using, what is it, Command Control E, mirrors it. That worked pretty well. Let me just drag this thing up a little bit more so that they're lined up. Okay, and then the next thing I'm going to do is delete this wire and add this wire. I should have memorized all these things. And then I'm going to duplicate, I need to, this out label here connecting this to that is actually means they're shorted, so I want to delete that because that won't work. And then I need a voltage source on the left, so I'm going to make a copy of VDD and just stick it right up there. And I think this thing is biased correctly now. Okay, so what you can see is that this current flows into this current flows down into here, establishing this voltage, which is just the right value of VGS to get M7 to carry the appropriate current. Notice that this voltage is 3.5. The minimum value that this voltage here could have been is about 0.36 plus 0.25, which is about 0.6 volts. If we make this about 0.6, give it a little bit of room just so I can, that'll probably work. Should be pretty close. And if we simulate this thing, notice that these two voltages here are the same. The VGSs are equal, everything is matched. So this voltage can actually go somewhat lower than the value of this, which of course we could have lowered this VG2 just slightly, but we need a little bit of tolerance for everything. So I hope that clarifies the issues about MOSFET biasing and how current mirrors and cascodes and low voltage current mirrors work. If not, please ask me some questions and I'll be happy to talk to you about it.